Right, we are going to be solving for the reaction forces as well as the shear force and bending moment diagram for the cantilever beam shown on the diagram. You can see that it's subjected to a concentrated load of 19 kilonewtons acting upwards at 2 meters from the fixed support, as well as a uniform distributed load that is acting on the last 2 meters of the cantilever beam. Now remember that a fixed support always prevents translation and rotation, so therefore we are going to have two reaction forces along the horizontal and vertical directions. We don't know the direction of those forces yet, so we are going to be assuming that they are directed towards the positive direction of the x and y axis. And then there's going to be a reaction moment, MA. Again, we are going to be assuming that it is counterclockwise positive, following the right-hand rule. So our thumb is directing towards the positive direction of Z that is coming out of the screen, and the hand is following the rotation counterclockwise. And this moment reaction, what it's doing is preventing rotation at support A. Okay, so once that we have the reaction forces on the diagram, what I'm going to do is calculate what would be the statically equivalent load of the uniform distributed load of 3 kilonewtons meter, and we know that that distributed load is equivalent to the area under the distributed load, so that would be the 3 kilonewtons meter times 2 equal to 6 kilonewtons. And for moment purposes, we are going to assume that it's acting at the geometric center of that distributed load. So basically it's acting at 2 meters divided by 1 meter. Okay, so we have now the free body diagram. We proceed to write the equations of equilibrium. So our first equation of equilibrium is summation of forces along x. The only force that we have here is the potential reaction at support A. And since we don't have any force component along the horizontal, right away we see that that reaction force is equal to 0. That doesn't mean that that support cannot develop a reaction force along the horizontal. It's just that for this particular loading condition, there is no AX. The next equation of equilibrium would be summation of forces along the vertical direction. So we have the reaction force AY, the 19 kilonewtons acting upwards, and then we have the statically equivalent load of the uniform distributed load, minus 6 because it's acting downwards. So the summation of all those forces has to be equal to 0. So from there we can deduce that the reaction force AY is minus 13 kilonewtons. And the minus is just telling us that in reality that force is not acting upwards as we had assumed, is acting downwards. And finally, the summation of moments equations. I'm going to take moments about support A. So therefore the two reaction forces AX, AY do not produce a moment at A. The first thing that I have is the reaction moment MA. I'm assuming everything that is counterclockwise is positive and everything that is clockwise negative to add and subtract properly. The next moment that I have at A is that caused by the load of 19 kilonewtons, so that would be counterclockwise rotation, and the moment is 19 times the distance, which is 2. And then I have the moment caused by the distributed load. Because it's acting outwards, the rotation with respect to A is going to be clockwise, so therefore I have a negative sign. And the value would be 6, the statically equivalent load times the distance, so it's acting at 5 meters from the fixed support. I equate that to 0, and from there we find that MA is minus 8 kilonewtons meter. Again, the minus sign here is telling us that the moment is in reality not counterclockwise, but it is clockwise. Okay, so once that we have the reaction forces and moments at the support, we are going to be drawing the corresponding shear force and bending moment diagrams. So here I have a free body diagram of our beam with the reaction forces with their values and the correct directions of those forces and moments. And the first thing that I'm going to be drawing is the shear force diagram. Remember, a shear force diagram is just a diagram that gives me a variation of the shear force along the span of the beam. And to draw this diagram, I'm going to remind myself that the variation of the shear force with respect to x is equal to the negative of the distributed load, the expression that I have on the right. So the first thing that I'm going to do is start from support A and moving along to the right. And I find the reaction force of 13 kilonewtons going downwards. A concentrated load, it always translates into a jump in the shear force diagram. And because it's going downwards, the jump is going to go downwards as well. And therefore, the value of the jump is the value of the force. Since I'm starting from 0, I end up with a value of minus 13 in the shear force diagram. Now I'm going to be looking at the load diagram for the next 2 meters, and I find there is no distributed load applied. So therefore, according to the expression that we have on the right, the slope of the shear force diagram is going to be 0 because W is 0, which means that the diagram is going to have a horizontal line for those 2 meters. Now at 2 meters we have a concentrated load of 19 kilonewtons going upwards. So again, there's going to be a jump in the shear force diagram with a value of 19. So we are going to go from minus 13 plus 19, and we end up with a value of 6 kilonewtons. For the next 2 meters, again, we don't have distributed load, so the slope of the shear force diagram is 0. That means that we still have a horizontal line, and the shear force remains at 6 kilonewtons. For the last 2 meters of the cantilever beam, we have the uniform distributed load. So that means now that the shear force diagram is going to have a constant slope of 3 kilonewtons, and it's going to be negative. And the only way that can translate is into a straight line with a negative slope of 3. Now, how do we know it goes back to 0? Well, the shear force at 6 meters should be the 6 that we started at 4 meters minus the area under the distributed load. So therefore, it would be 6 minus 3 times 2, 6, equal to 0. So we have closed the diagram to 0, and it's just a confirmation that our system is in equilibrium. Now that we have the shear force diagram, we can move on to the bending moment diagram using the relationship between bending moment and shear. So we know that the slope of the bending moment diagram is the shear force. So again, we are going to start at support A, and we will be looking at the shear force diagram to find out what is the bending moment diagram. But also remember that every time we have a couple or a moment acting on the beam, the same thing that we have a concentrated load translating to a jump in the shear force diagram, a couple or a moment will translate into a jump in the bending moment diagram. So we have the 8 kilonewtons meter that is acting clockwise in our load diagram, but in reality what that moment is doing, and I hope you can see that, is compressing the top of the beam and pulling or extending the bottom of the beam. So we basically have compression at the top at point A and tension at the bottom. That is what we call a positive bending moment diagram. So therefore the jump of 8 kilonewtons meter is going upwards. Okay, and then the value of the moment is 8. Now we continue moving to the right, and now we concentrate on the shear force diagram. So the shear force for the next 2 meters is a constant value of 13 and is negative, which means that the slope of the bending moment diagram is going to be constant and negative So that's a straight line with a negative slope of minus 13. The value of the moment at 2 meters would be the 8 meters that we started with minus the area under the shear force diagram. So that would be 8 minus 13 times 2. We end up with a value of the moment of minus 18 at 2 meters. Now we continue for the next 2 meters. We observe that the shear force is 6, positive, constant. So therefore, the slope of the bending moment diagram is going to be, again, positive and constant. So we are going to have a straight line of a slope 6. And the value of the moment at 4 meters is going to be the minus 18 that we started with, plus the area under the shear force diagram for those 2 meters. So that would be minus 18 plus 6 times 2. We end up with a value of minus 6 kilonewtons meter at 4 meters. Now, finally, for the last 2 meters, we observe that the shear force diagram is positive, but the value of the shear force is linearly decreasing from 6 to 0. So it's positive but decreasing from the right to the left, which means that we have to have the slope of the bending moment has to be positive and decreasing from the right to the left. And because we have a linear function for the shear force, when we look at the bending moment diagram, through this relationship, we know that the moment would be the integral of the shear force, which means that we would end up with a quadratic function, a parabolic function. And to determine how that parabola is going to look like, remember that the slope of the parabola has to be positive because the shear force is positive, and that slope has to decrease as we go from the right to the left. And this is how it would look like. Now, how do we know that it ends up in 0? Well, what we can do is, again, calculate the moment at 6 meters. So that would be the minus 6 that we start at 4, and then plus the area under the shear force diagram, which in this case is a triangle. So we end up with minus 6 plus 6 is the height of the triangle times 2, the width, divided by 2. We end up with a value of 0. So here you have the shear force and bending moment diagrams for this beam. We can see that the highest shear force acting on the cantilever happens at support A, and the value is 13 kilonewtons. And the highest bending moment acting on the beam acts at 2 meters from the support, and the value is 18 kilonewtons meter. Is negative, which means that the top of the beam is under tension and the bottom of the beam is under compression.